Ok. Bah, ça m'a l'air bon. On va attendre 9 heures.
Good morning, Ludovic. Do you hear me? It's okay for you? Oui, il manque juste une personne qui répondra pour le moment. Tout le monde est connecté en tout cas. Oui, oui. Il y a personne d'autre que le jury en visio. Là. Professor Seifer, is it okay for you? Do you see the screen and do you hear me? Okay, so we will wait for the moment. Juste un truc, Nico, tu pourras peut-être leur dire au moment des questions, essayez de prendre les micros pour que ce soit capté sur le live YouTube.
Ok. Au moment où il va parler, de toute façon, après...
Mais voilà. Et du coup, là, c'est bon, niveau admin, les délégations de pouvoir et tout ça te place, hein?
Bon, après. Parce que j'ai vérifié dans le mail, on dit qu'on fera après. On m'a donné les trucs à signer, pas de problème. Ouais, okay. C'est bon, il a dit que c'était bon, lui.
Ok.
Merci.
Okay, so it seems it's good for all of you. So we will wait a bit in the room, time for the people to sit, and we can start if it's okay for you.
C'est bon.
Bon, bonjour à tous. Mon nom c'est Jean-Paul Villas-Boas. Je viens de Porto et c'est un grand plaisir d'être ici. C'est un grand honneur et je veux commencer par présenter mes compliments personnels et les compliments du directeur de ma faculté et du recteur de mon université aux autorités de l'Université de Rennes 2. On est ici pour la défense du doctorat d'Antoine BOUVET, titulé Swimming Monitoring and Modeling for Performance Using Inertial Measurement Units and Data Science. Et on a un jury qui je présentera en continuation. Je demande permission pour changer du français à l'anglais, même parce qu'on a des partenaires de jury qui peut-être préfèrent l'anglais au français. De toute façon, merci beaucoup pour m'avoir ici. Let's change to English. This PhD defense will be assessed, evaluated by a jury composed by two Italian professors, Professor Maria Francesca Piacentini from the University of Rome, Foro Italico, Professor Silvia Fantozzi from the University of Bologna, a very distant member of the jury, Ludovic Sefer, qui est, I'm sorry, today in New Zealand. Good evening, Ludovic. Professor Salima Alcolé, Professor Nicolas Bidot et Professor Mathieu Marbach. I take this opportunity to present also my compliments to the candidate and to the public that gives this public nature of the defense process. And I present also my compliments to the promoters of the thesis. And last but not least, to Antoine. It was a real pleasure to read your thesis, and I think that everything went very softly and very well, in accordance to your best expectations. So for the start, we have to give you the word for at least 45 minutes, at the end 45 minutes, I think, to introduce us in your thesis.
Okay, thank you for the introduction, Professor Villas-Boas, and good morning, everyone. Thank you for being here on this special day for me, and thank you to the members of the jury who have agreed to judge my PhD thesis. I'm very pleased to present to you my research work entitled Swimming Monitoring and Modeling of Performance Using Inertial Measurement Units and Data Science, Methodologies and Applications for Scientific Support of Performance. In the age of the digital revolution, swimming is still under-technologized. However, the densification of elite swimming requires more and more optimization of the training process and a detailed analysis of competitions. The use of embedded sensors, such as inertial measurement units, makes it nowadays possible to monitor swimmers on board. Nevertheless, their use poses obstacles in extracting swimmer-relevant metrics from raw signal related to the swimmer's motion. The aim of this PhD is therefore to develop a biomechanical monitoring toolbox to scientifically support the performance of French swimming teams under ecological conditions, including performance modeling and technical stroke regulation profiling. So let's dive on this research journey together. My PhD work, summarized under the acronym SwimUp, is part of a national research agency priority research project called Neptune. Its aim was to provide scientific support for high-performance swimming in the run-up to the Paris 2024 Olympics, in collaboration with the French Swimming Federation. The idea is definitively to put academic research at the service of French elite swimming by transposing scientific developments in a way that is adapted to the constraints of the field. As part of a consortium, our role in Rennes has been to develop in situ motion analysis solutions tailored to the pool and the open water environment. Motion analysis in swimming is an essential part of the quest to optimize performance, as reducing the energy costs through technical reorganizations often yields greater performance gains than increasing the metabolic power. However, such analysis is generally very laborious because it is carried out using highly complex systems that are not designed for in situ tracking during daily training and competition context, thereby limiting their use to a laboratory context, as you can see here. Additionally, World Aquatics rules now allow the wearing of onboard sensors in competition, further reinforcing the need to develop dedicated monitoring solutions adapted to training and racing situations. So this is the background to our work, which aims to meet the demand for user-friendly motion analysis in the field. The biomechanical data then collected can be used in a variety of ways, including training monitoring, performance modeling, and also race analysis. The requirements imposed by elite swimming are very restrictive and must fit into the concept of invisible monitoring to minimize the burden of measurements onto athletes. The tools proposed must be used by coaches and not interfere with movement and feelings of water. Additionally, data processing must be rapid and easily lead to ready-to-use insightful technical reports, which means translating biomechanical data, sometimes derived from complex statistical models, into directly interpretable feedback for practitioners. Finally, the methodological solutions proposed must be robust and generalizable, that is, taking into account intra- and inter-subject variability in kinematics in order to suit swimmers who are very different and to adapt to evolving situations, including fatigue and variable intensities. At the same time, our work is based on the observation that swimming is still an under-technologized discipline. There is a lack of data and sensor culture, which translates into a strong reluctance to integrate them routinely, as can be seen in this quotation of Nicolas Castel in 2021. However, the current densification of elite swimming requires ever greater individualization of the training process and a detailed analysis of competitions. We therefore believe that the contribution of data-driven approaches could be a catalyst for improving the technical expertise of coaches and also race strategy settings. But for this to happen, we still need to be able to collect metrics of interest, so the famous key performance indicators, KPIs, and then to use them to understand performance requirements. Looking at the pool KPIs, they are derived from the different phases of the race and are aggregated according to different types of analysis. Particularly, the spatiotemporal parameters related to stroke mechanics, such as stroke rate and length, are crucial for understanding the continuous regulation of pacing throughout the race. Additionally, motor variability appears to be a key feature of cyclical human motion, but is still underexplored to discriminate the global effectiveness of stroke technique, whereas swimming smoothly is a common coaching directive and a sensation sought by swimmers. Such stroke smoothness can be quantified by the GR cost. Automating the collection of these metrics can drive technical training and discriminate in race regulations. Additionally, the construction of large databases will subsequently pave the way for new data-driven modeling approaches across race distances, as well as profiling intra- and intercyclic kinematic variability. In terms of the tools available to collect these KPIs, they are mainly unsuitable for routine monitoring with rapid feedback, as they involve manual or semi-automated treatments and do not provide access to all the metrics of interest, such as the stroke smoothness and the cyclic motor variability. As a result, the main technological monitoring solutions for swimming can't meet the practical challenges previously mentioned. Nevertheless, in this ecosystem, the portability of IMUs, combining a 3D accelerometer, gyroscope, and magnetometer, is an interesting logistical avenue to explore for onboard measurement of swimmer motion in ecological conditions. Looking at the open water KPIs, they are broadly similar to those for the pool, to which we could add spatial parameters related to the swimmer's position in the pack and any currents. Also, there is only front crawl. Open water monitoring has many other constraints with very complex conditions. The literature focuses mainly on the analysis of the pacing, but without providing insights into the associated regulation of the stroke mechanics to explain it from a technical viewpoint. Furthermore, these analyses are based on time data and fragmented analysis, which ultimately limits the understanding of performance requirements. Therefore, it is of utmost importance to develop methodological solutions that allow the continuous monitoring of stroke mechanics and kinematic variability during open water races. In terms of the technological tools available, the same observations can be made as in the pool, but they are even more exacerbated by the constraints of the natural open water environment, as you can see on the video. As a result, coaches and staff simply don't have kinematic data on swimmers' performance, and finally can't objectify and track swimming technique. Again, the contribution of IMUs is promising in terms of improving scientific support for performance and collecting technical data to model and better understand the effective conservative pacing strategy reported in the literature. So we see that IMUs offers an interesting perspective for swimming monitoring and performance modeling. Nevertheless, these onboard sensors do not provide the KPIs directly, as shown on the right side, but rather a highly sampled multivariate time series related to the swimmer's three-dimensional acceleration and angular velocity, as shown in the middle. Then, such data have to be processed. Our work, therefore, aims to provide data science contributions to extract performance and technical variables from these complex signals, which evolve according to the swimmer's activity. After that, we can then apply such KPIs. On the one hand, with the French Swimming Federation for scientific performance support, and on the other hand, to advance swimming research in terms of understanding of pacing strategies, but above all, of the underlying profiles of stroke mechanics regulation and cyclical kinematic variability. In this thesis, academic research is positioned as the fulcrum of scientific performance support. This involves, firstly, research phases to develop classification and clustering algorithms for performance monitoring and modeling based on 3D kinematics recorded by a single IMU. Secondly, we are implementing a field transfer phases of this biomechanical toolbox. And this framework involves high scientific stakes and poses a number of methodological obstacles to transform in a generalizable way the raw IMU data into tailored swimming knowledge. To this end, the use of advanced processing tools such as artificial intelligence-based methods could unlock the power of IMUs as a biofeedback tool in swimming. Otherwise, statistically based methods such as functional data analysis appear to be an exciting way of dealing with IMU curves and associated KPIs while preserving their continuous nature. Such time series model may address the practical challenge of elite swimming monitoring and ultimately meet the specifications for effective scientific performance support. Here you can see the applications of this general framework to the scientific contributions proposed as part of this thesis. So let's go into the details of these different studies, starting with the methodological contributions to the monitoring and modeling of swimmers' performance, and then looking at their practical applications, both to current issues in sports science research and to the scientific performance support of the French open water swimming team. So the first methodological step was to develop a tool for swimming activity recognition using a single IMU. We have developed a generalizable deep learning model that can accurately recognize the different phases of a swimmer's activity in the pool. Its advantage is that it allows the activity to be segmented to facilitate the automatic collection of KPIs such as lap time, stroke rate, length, and stroke smoothness relative to movement efficiency. This really opens the door to simple in-situ monitoring that meets the needs of trainers. In order to provide a robust analysis by automatically recognizing the different phases of swimming, we train a neural network on 35 heterogeneous swimmers who perform the protocol including all possible activities and at different intensities in order to maximize the variability. We recorded sacrum IMU data synchronized with video used as ground truth, and this results in approximately 950 minutes of manual label data as input to the classifier. The strength of this database lies in its ability to take into account for a wide range of intra- and inter-subject variability. In fact, we have included swimmers from recreational to international level and across the full range of existing intensities. As a result, we have a classification model that adapts very well to swimmers who are unfamiliar with the initial training and is capable of predicting activity to the nearest 200th of a second in 8 cases, so namely the 4 swimming styles, the rest, the turns, the underwater phases, and the wall push. Additionally, the automatic calculation of lap times is directly derived from the model's prediction. Here is an example of the data collected and the corresponding phase labels on 100 medley. The first 2 plots correspond respectively to the acceleration and angular velocity in 3 dimensions, and the last plot refers to the activity, the true activity performed by the swimmer. As illustrated here, through the underwater phase, each activity has a specific inertial signature, and this is the basis for learning the model to perform activity prediction. Below, you can see the architecture of the model, which uses 4 layers of B-long short-term memory units, as well as various dropout and recurrent dropout settings to avoid overfitting, and batch normalization to facilitate the training in the deeper layer. In terms of the model's performance, we can maintain a satisfactory overall F1 score of 0.96. However, the activity recognition performance varies from one class to another and is particularly low for very short phases such as wall push. This can be explained by the fact that this phase lasts only a few tenths of a second and has a reduced sample in the database. However, this does not prevent the model's output from being used to monitor swimmers. The calculation of lap times is sufficiently accurate, so similar to a manual stopwatch, but automatic. Note that the last length of an interval is less accurate because the model has some difficulty detecting the swimmer's last end touch on the wall. And this work is the first to investigate such a discrepancy in accuracy between types of lap time. In conclusion, the model developed allows the segmentation of swimming activities and the automatic calculation of lap times. Additionally, through the recognition of the swimming phases, it facilitates the consequent calculation of the decisive KPIs. Finally, its high recognition performance opens the door to automatic tracking by means of rapid feedback and minimization of the burden of measurement. Then the French Swimming Federation has used it extensively in the field. Here is a demonstration clip, so installation is extremely quick, does not disrupt the normal training, and the model can be used to extract spatiotemporal parameters. We can then propose an individual biomechanical profile to identify each swimmer's strengths and weaknesses using such kind of radar plot, for example. By providing KPIs at each pool length, the model offers the possibility of quantifying regulation of stroke mechanics in fatigue situations, as well as longitudinal progress. Finally, this large amount of data opens up the possibility of modeling swimming technique in order to define individual training paths. Now that it is possible to easily monitor performance for scientific support, this first methodological development also raises the question of performance modeling and race analysis for sports science research. So let's look at 2 contributions in this respect. The ability to easily collect large amounts of data allows us to explore innovative research questions. For example, identifying the mechanics of swimming that underpin and discriminate pacing effectiveness is a major challenge in understanding the determinants of performance and therefore the training of distance swimmers. We have shown that specific regulatory profiles in terms of a dynamic trade-off between the smoothness of the stroke pattern, which defines the mechanical efficiency of the movement, and the resulting speed, defining the performance, lead to optimal pacing during a 5K pool races. This work is motivated by the fact that pacing strategy is crucial for successful competitive results, and especially in long-distance events. In such races, pacing optimality can be defined physiologically and theoretically as the ability to maintain the highest possible fraction of the individual critical speed. However, in swimming, achieving such an optimal potential performance level seems highly dependent on the underlying technical characteristics, especially throughout the continuous adaptation of stroke mechanics over the race. Therefore, the present study aimed to identify the technical regulatory mechanisms of distance swimmers that differentiate optimal pacing strategies. To do this, we analyzed 5K races of 21 elite swimmers. We used our previously described human activity recognition model to compute KPIs at each lap. We then automatically identify groups of pacing effectiveness using a functional clustering of the ability to maintain critical swimming speeds throughout the race using a conventional algorithm of the literature. Finally, the regulation of stroke mechanics defining technical abilities common to all swimmers, as well as specific and discriminant deviations by groups of pacing optimality, were modeled using hierarchical generalized additive model. As a result, we identified two clusters of pacing effectiveness, which we call near and far from the optimal potential performance level. This analysis makes it possible to identify the specific race management and pacing skills of optimal performers that need to be developed in training. That is, race sections with a more stable global pacing and enhanced spurts of higher magnitude. However, one may wonder about the technical adaptations of stroke mechanics that support such optimal pacing. Hierarchical generalized additive models provide an interesting framework for answering this question. On the left, you have the all swimmers plot, which describes the common relationship that holds for all swimmers in the database, regardless of their pacing group. Next, you have two panels describing the cluster-specific deviation from this common relationship, with one plot for each pacing optimality group. Such statistical models highlight discriminative biomechanical abilities of optimal performers, and these are firstly the maintenance of a higher stroke length in the fatigued states, and secondly, a high degree of regulation of their mechanical proficiency from an economy-oriented to a speed production-oriented swimming technique, and interestingly in line with the pacing expectations of particular and evolving race sections. Suboptimal performers are not able to regulate their stroke pattern in such a way. Finally, we provide avenues for technical explanations leading to better durability in long-distance swimming. Such findings raise promising questions for the understanding of a current hot topic as durability in swimming, and in particular about the potential interactions between physiological resilience and stroke mechanics, especially through the adaptation of stroke smoothness. This study takes advantage of our activity recognition model to combine and link both pacing and stroke mechanics profiling in an innovative approach to sports science. We highlight key race features and underlying kinematics for achieving optimal performance that should be targeted in the training of distance swimmers with evolving technical constraints in fatigue situations. Let's now look at the second contribution from sports science, which exploit the ease of collecting KPIs in situ. In the same vein, the aim is to highlight game-changer technical regulations of stroke mechanics that support effective pacing and final performance, but this time using a different methodological choice that is not a data-driven approach, but a process-driven approach. In fact, current race analysis focuses mainly on effective pacing strategy, but without biomechanical understanding of them. This restricts insight into the stroke regulation pattern that drive performance at different levels of competition, while limiting the identification of key technical skills determining progress. We have therefore developed a framework for in-situ modeling of pacing and associated stroke mechanics using a single embedded sensor, which we apply to 400-meter front crawl race simulation. The kinematics enabling a successful conservative pacing in middle and long-distance swimming remain unclear and limited to sparse data modeling, whereas fine-tuning of pacing seems highly dependent on technical skills. This study aims to identify the stroke mechanics regulations that underlie pacing optimization and differentiate final performance across different performance levels. To do this, we need to model both the common trend shared by all swimmers, so for example, is the black curve on the graph, but also the specific deviations that distinguish performance groups. So this is the colored curve shown here on fishes species. Once again, hierarchical generalized additive models appear to be a promising statistical framework for identifying both joint and group-specific benchmarks. To this end, we analyzed 157 trials of heterogeneous swimmers performing 400-meter race simulation with an IMU located on the sacrum. Based on their final performance, we created 4 balanced groups in number, age, and sex. The IMU signal was processed to extract lab-to-lab KPIs, and we used hierarchical generalized additive models to analyze these variables in different ways. Firstly, to provide kinematical predictors of overall performance, relationships between each average variable of stroke mechanics and the mean speed were fitted. Secondly, to evaluate and compare the pacing profiles as well as the associated stroke control across the race, relationships between either speed or each of the mechanical variables as a function of laps were fitted. Here is the model relationship between each average mechanical variable and final 400-meter performance. So firstly, for the stroke rate performance relationship, we show a non-significant negative association, but interestingly, we have a range of performance maximization for the fastest swimmers. Secondly, for the stroke length performance relationship, the model displays a significant logistic shape. Average stroke lengths increase continuously from the lowest to the highest performers, except between G2 and G3, while the stroke rate is simultaneously higher for G3 than for G2, suggesting that the mechanical reorganization driving performance development are level specific. Finally, the relationship between jerk cost and performance shows a significant positive link, but it's attenuated for G1 and then emphasizes their low technical quality. In addition, there is only a difference in average stroke smoothness between G2 and G3, highlighting the discriminating technical ability of the fastest swimmers through an improved mechanical efficiency. Now let's look at the pacing and stroke mechanics of the race. We can observe a common reverse G-shaped pacing as traditionally found in the literature. The fastest swimmers reduce pacing variability with a relatively slow start, a minimized drop in speed in the middle of the race, and a greater end spurt than the population trend. Let's see how their stroke mechanics are effectively adapted through these specific and then evolving race sections. We firstly see a continuous balancing of the stroke rate-stroke length combination according to the requirements of the race phases. Particularly, an exacerbated stroke rate reserve differentiates the top performers, while the lowest performers can't effectively align their stroke mechanics to the evolving pacing demands. Secondly, the accentuated U-shaped jerk cost of the fastest swimmers suggests that the regulation of stroke smoothness is a discriminative technical skill that drives performance and then needs to be targeted in training. This work provides coaches and staff with objective data to guide the training process and design specific training sessions. Interestingly, we observe a kind of contradiction with strong implications for training. For an apparent pacing stability, the underlying technical regulation of swimming mechanics must be maximized. From a practical viewpoint, the benchmarks provided suggest that technical skills, as evidenced by the stroke smoothness at race pace, is critical for the progress of elite swimmers. Finally, we can easily imagine extending this tool, combining a single embedded sensor and a statistical model to other swimming distances and disciplines, and to an individual approach with chronic race comparisons of one swimmers. It then offers interesting perspectives to enrich the field of swimming race analysis. Let's move on to the second data science contribution. The collection of large amounts of in-situ IMU data has opened the door to questions about dedicated statistical modeling of swimming technique. The work ahead will attempt to answer these questions. We will then look at the field application of such a statistical model to provide relevant biomechanical abilities during sprint front crawl swimming. In short, it represents a valuable opportunity for swimming research and more generally for the analysis of cyclic human motion to enrich the 3D kinematic profiling of technical skills through both intra- and intercyclic variability. This data science development contributes to a practical problem in the training of swimmers, namely the evaluation of their technical qualities. Based on IMU recordings, a statistical clustering model of multivariate functional data captures kinematic variability to objectify swimming technique, a concept that remains very subjective in the field. This tool enriches the expert eye of the coach with a data-driven approach by allowing a better profiling of technical skills through an automatic and a user-friendly framework. The monitoring of technical skills in swimming is fundamental, and the literature agrees that the notion of stroke variability is a critical factor. This variability is twofold, both within a swim cycle, so it's the stroke pattern, and between swim cycles, so it's the dispersion or the reproducibility of the stroke pattern. The multivariate time series provided by the IMU makes it possible to collect objective biomechanical data, which are functional data, relating to this movement variability. The aim of this work is to provide an automatic stroke profiling tool to assist coaches in biomechanical monitoring. From a statistical point of view, the aim is to perform a double functional clustering, considering the specificities of this real-world swimming data. double because we want to capture both sides of the biomechanical variability, so the average stroke pattern and its dispersion, which is already a first specificity of our data. These specificities can be seen in the following graphs. On the left, we have the raw front crawl data with the 6 IMU dimensions for 2 swimmers. And on the right, you have the same thing, but for cycle normalized data with a recreational swimmer in blue and an international one, a recreational in red and an international one in blue. So we can see differences, firstly in the shape of the curves between red and blue, which refers to the stroke pattern, so the intracyclic variability, but also in the thickness of the curves, which refers to the dispersion of the average stroke pattern, so the intercyclic variability. Finally, the dependency between these two complementary criteria contributes to the notion of technical quality, since the difficulty of reproducing a swim pattern naturally depends on its shape. It will therefore be necessary to model these two characteristics in the data, as well as their dependency. To do this, we use a classical approach by decomposing the data into functional bases. The modeling is such that the random coefficients YA depend on an unobservable VA that define K tips of stroke pattern, and the random coefficient ZA depend on WA that define L abilities to reproduce the stroke pattern. The functional basis coefficients follow a mixture model that allows to doubly cluster the swimmers and take into account the dependence between the two partitions V and W, since this is necessary in our context, as can be seen in the PKL. We therefore perform a dual Fourier basis function decomposition that considers both the original signals x and the residuals epsilon for each IMU dimension g. This is definitively a major difference from traditional approaches in literature that generally consider residuals only as noise. In swimming, however, both decompositions are necessary because the first one refers to the stroke pattern over the YA, so the intracyclic variability, modeled as this red regression line, and the second refers to the ability to reproduce this average stroke pattern over the ZA, or its dispersion, so the intercyclic variability modeled as this second red regression line. Methodological considerations regarding parameters identifiability, parsimonious model block variable selection, model estimation and selection, as well as numeric simulations are not detailed here to focus on the sports science implications. Indeed, we applied this double clustering model to a real data set of front crawl sprint swimming, including 91 swimmers from a local level to a French world champion. The clusters resulting from the two partitions are technically analyzed to give them a biomechanical meaning. And to complete the interpretation, we will establish the link between these clusters representing specific swimming technique, or basically way of moving in water, with performance. Here is the main visualization of our application with IMU dimensions in the rows, 3D accelerations on the left, so longitudinal, mediolateral, and antero-posterior acceleration from top to bottom, and 3D angular velocities on the right, so rolling, pitching, and yawing speed. In the columns are the different types of cluster in the stroke pattern, and in colored area are the different kind of dispersions around them. The clustering on the intercyclic variability leads to 3 clusters of dispersion ordered from a low to a high level of stroke pattern repeatability. Note that this dispersion is not constant over the swim cycle and show interesting variations at specific points on the average pattern curve, indicating that the intercyclic variability is greater during the critical propulsion phases of the cycle, as shown here on the longitudinal acceleration. The clustering on the intracyclic variability leads to 2 clusters. The first, called jerky on the right side, represents an irregular swimming pattern with large intracyclic variations in both longitudinal and antero-posterior acceleration. And the second, called smoothie on the left, is represented by a more fluent swimming pattern. This greater regularity of motion may lead to a relatively low energy cost of swimming, but also in fewer speed production. If we associate these partitions with swimming speed, we can make observations about the appropriate motor organization. Indeed, both the jerky swimming pattern and the high dispersions are significantly more associated with swimming speed, with sprint swimming speed, than the other clusters, despite decreasing the mechanical efficiency. When we cross the two partitions, it is naturally the cluster that associate both a jerky swimming pattern and a low reproducibility that seems to be the most effective biomechanical strategy to technically respond to the high demands of sprint swimming. Also, it may seem counterintuitive that higher level of variability is relevant. This swimming technique actually leads to efficient outcomes for a highly specific task like a sprint task. In conclusion, we present a model that allows the monitoring of technical skills in real-life situations using a single IMU by adequately capturing the discriminative components of motion variability. This tool offers new possibilities for automatic and non-invasive classification of cyclical movement through their kinematic variability, which is a hot topic in sports science, both for performance optimization, but also for medical and rehabilitation applications. This approach can also be used to visualize technique only, that is without the clustering part, but only the double functional decomposition. And in this way, the French Swimming Federation routinely used it extensively as a scientific tool to support performance. Here is a recent example of March of how we combine video and IMU data to perform technical profiling. As you can see, the visual observations of the swimming technique can be quantified in the IMU signature, allowing us to objectify the motions in water. For this swimmer, there is a major problem with the integration of his bracing into his motor organization, which affects the vertical oscillations that we can see on the antero-posterior acceleration. This other point of view offers another possibility for technical optimization linked to a too long in-breath timing impacting side-to-side jerks, which we can also track in the IMU curves through the mediolateral acceleration. So we can model such a baseline in the kinematics and then follow the progress and the evolution during training. In short, it's definitively a user-friendly tool that helps swimmers and coaches become aware of the impact of movement in the water on 3D kinematics. Finally, let's move on to the last scientific contribution of this PhD thesis with the profiling of the stroke mechanics regulation in open water that leads to a descriptive performance model for world-class open water races. Strikingly, this work did not require any major methodological developments. Nevertheless, it is probably the work that has had the greatest impact on the field with the French Swimming Federation. This study analyzes cycle-to-cycle stroke rate and jerk cost time series data from IMU recordings during international open water races. The aim is to profile trends in stroke mechanics while determining the dependency of these regulatory times on final performance. These are the first continuous measurements taken during official competitions and represent a step forward in the understanding of performance, related technical organizations, and also race analysis. It also provides valuable data for tailoring training sessions and identifying future talent for the next Olympics. Race analysis in open water swimming has typically identified optimal pacing as a conservative approach. However, the technical explanations underlying these race dynamics are of crucial importance, but remain unclear, particularly as the literature is mainly based on official time data with limited resolution. Therefore, it is crucial for both swimming research and for scientific performance support to continuously monitor the regulation of swimming mechanics during open water races. This may provide insightful explanations of relevant pacing that can be incorporated into targeted training and race strategies. That's why we developed a framework for in-situ kinematic analysis using an IMU. Based on a data collection covering 5, 10, and 25 kilometers during international races, we construct 3 performance groups. G1 including the top 5, G2 from 6th to 10th place, and G3 above the 11th place. We extract from the IMU signal cycle-to-cycle stroke rate and jerk cost data. And finally, their normalized time histories were fitted using non-parametric regression to assess kinematic profiles and tipping points in stroke regulation timing by performance groups, as you can see on this slide. Here you can see the fitted profiles for the 3 performance groups in terms of stroke rate on the left and jerk cost on the right. The curve shapes are clearly different, highlighting a specific patterns of stroke control by performance groups throughout the race. As you can see, 2 tipping points structure the stroke regulation and then define 3 race periods. Firstly, there is an economy period in which stroke rate and jerk cost decreases, potentially by taking advantage of drafting in the swimmer's peloton. Secondly, there is a progressive increase in mechanical parameters. At this point, G1 and G2 profiles are not very different, even if the G1 swimmers are able to sharpen the stroke economy period. And thirdly, the main difference occurs at the second tipping point, when the first 5 swimmers are able to maintain the kinematic increase supporting end spurt launching for the final sprint, whereas swimmers from the 6th position onward are not able to do so. And these discriminative regulations are facilitated by superior technical skills reflected in a significantly lower overall gear cost of successful swimmers and the ability to convert stroke smoothness degradation into higher speed when needed. In conclusion, this work illustrates the usefulness of a single EMU-based monitoring in the real context of world-class open water racing. It provides coaches and staff with objective data on kinematic regulations throughout the race, driven by a high grading dynamics. These findings have important implications for the development of discriminating technical skills through training sessions aimed at, firstly, the so-called stroke rate reserve to allow a fast end spurt, and secondly, a race period-specific stroke smoothness control. Finally, this descriptive performance model was used to prepare for the Paris Games through data-driven race analysis. It is also being used with the junior generation to design test sessions and training sets that reproduce the expectations of international races. So let's take a look at some examples of scientific performance support using our developments. We are able to provide race reports and overview like this. Here is a comparison of 2 races, the Junior World Championship with a win and the Senior European Championship with a 10th place. The races are analyzed according to the stroke mechanics regulation with comparisons to our top 5 model in blue. And we can see from the black lines that Sasha is far from the expected kinematics at the beginning of the race in the Senior European Championship, especially if we look at the gear cost trend. Then he pays for it later when the pace increases. In contrast, during the Junior World Championship in red, Sasha is able to perfectly fit into the performance model and won the race. The races are also analyzed in terms of 3D kinematics using the functional data analysis framework described previously, but this time focusing only on intracyclic parts. Here we can see that during the Senior European Championship, so it's the red curve, Sasha presents large and a symmetric peak on the antero-posterior angular velocity. This may explain why Sasha didn't enter a period of stroke economy. Interestingly, during the World Junior Championship in blue, we can see that such technical characteristics have been corrected. The use of our scientific performance support tools therefore allow us to understand and quantify what happened during the race through this type of easy-to-use report for coaches and technical staff. This has enabled us to also collect and analyze some exceptional race data, such as the victory of a Frenchman in the 5K race at the last World Championship. Basically, this case study is full of lessons. In fact, despite a race management that is close to perfection in terms of stroke mechanics regulation, with a fast start for an early loading position, a better and longer stroke economy period, and a dramatic end spurt triggering to win, which clearly exceeds all the expectations of our top 5 performance model in all sections of the race, the 3D kinematic analysis show that there is still room for technical progress. For example, there is a large kinematic asymmetry in the longitudinal acceleration and a strong potential for improvement in the stroke efficiency as acceleration is widely oriented upwards rather than forwards, and especially during the in-breath timing. Then it induces very large pitching motions, which increases drag and then impair the energy cost. Sorry for that. The video and screenshot of the swimmer illustrate these detrimental motions, which are reflected in our modeled kinematic curves. The training culture in French swimming is often volume-oriented with very high training loads, prioritizing the development of metabolic power rather than the reduction of energy costs through technical work. The introduction of data has allowed us to quantify, track, and interestingly visualize these systemic shortcomings about the integration of bracing into stroke pattern. Finally, it raises the question of whether such practices neglect training quality through technical work, which I personally believe is an underexplored avenue for progress for many top French athletes today, as illustrated by the race data of this world champion and confirmed by specific video assessment during training. To conclude this presentation, a few summary points. We can conclude that the use of embedded sensors such as IMU and time series models such as deep learning and functional data analysis provide relevant technological and methodological avenues for performance monitoring and modeling that are adapted to the constraints of elite-level swimming training and competition. Then this thesis lays the foundations for the implementation of easy-to-use chronic monitoring based on the reality of current swimming practices. It then invites a more detailed understanding of technical skills and at optimizing the training quality process. In fact, this work now faces the challenge of being disseminated to coaches for a greater integration into their routine. The SwimUp toolbox allows a better understanding of pacing strategies and, above all, of the underlying technical regulation of both stroke mechanics and 3D intra- and intercyclic kinematic variability. This framework seems to be particularly suitable and relevant for use in long-distance pool and open water races where automatic data collection is very complicated. Some future prospects can be drawn. From a monitoring point of view, this will involve the coupling of several sensors in addition to the IMU. In particular, the use of GPS would allow a more detailed analysis of pacing and tactics in open water, and the use of near-infrared spectroscopy to assess physiological dimensions and link them to stroke mechanics. We have carried out some experiments along these lines with interesting and promising results. From a modeling viewpoint, recent contributions in the statistical literature on longitudinal modeling of multivariate functional data seem very promising for the analysis of IMU data with repeated measurements, for example, over the course of a race or a training cycle. It may be very interesting to quantify and track the onset of fatigue, technical deterioration, or skill progression, as we are currently do it only by visual observation of the curves. Finally, from the point of view of sports science research, the analysis of the interactions between technical regulations, physiological profiles, and performance determinants seems to be the logical continuation of this PhD thesis work for open water, and especially considering the fundamental role of durability in other endurance disciplines, such as marathon running or cycling. I'm coming to the end of my presentation time, so it's time for me to thank you for listening to me, and especially to the members of the jury, because it's a real honor for me to have my PhD evaluated by such international experts in the field of swimming research. I would like to conclude with two open questions that reflect the initial objectives of the Neptune project, in which this thesis is fully integrated. Namely, to provide swimming practitioners with tools to evaluate the key factors of performance, to identify different swimmer profiles in order to individualize training and to compute models to optimize motion. So, 1 year after the Paris Olympics, can we speak of a kind of sensor culture and a data culture in French swimming? And have we succeeded to creating together a common framework for scientific performance support? I'm ready to try answering your question and discuss about my manuscript and presentation. Thank you very much.
Thank you. If you want to say something else, you have 20 seconds left.
It's okay for me.
Thank you for sticking to the time available. And thank you very much for your very nice presentation, a difficult synthesis of such a huge PhD thesis with so much work. So in continuation, we will have from the other side of the world, Professor Ludovic Seyfer from the University of Rouen. Hi Ludo, I hope you feel fine there in the, you should be upside down, I think. You have 20 to 25 minutes talk with Antoine, so the floor is yours.
Thank you, Mr. President. Can you hear me correctly?
Yes, it's good.
Yeah.
Thank you. So first of all, I would like to thank the supervisor of this PhD for having inviting me for the examination of this PhD for this very, very good PhD. I really enjoyed reading the manuscript and also listening your presentation today. All the manuscript is very well constructed, interesting to read, well documented, good figures, very clear. So again, I really congratulate you for this work to meet a high level of achievement, and also because it's an interdisciplinary work, which is not easy to conduct with two supervisors in different fields. So I imagine a lot of discussion between data science and sport science inside. So for all this big work, again, I really congratulate this work made in 3 years and with almost 6 publications. So to me, it's a very high standard that you achieve. Obviously, I have some questions that interest me as well. So I'm happy to discuss with you this following question. So the first question is, you assume that the jerk cost must be minimized because it corresponds to a lower energy cost, so higher economy, but nowhere in the document you really show or even measure that the low jerk cost is associated to a low energetic cost, because finally you never collected physiological parameters, except in the perspective where you showed us that you assessed the oxygen saturation in the muscle. So my first question is, why not looking at energetic cost or any other physiological parameters against the jerk cost value?
Okay, so thank you very much for this very interesting but also challenging question, which has shaped many of our reflections through this PhD. I will divide my answer into 2 parts because your question is very challenging. So first, I will briefly review the motor control literature and the elements on which this hypothesis linking jerk minimization to efficiency, or at least the effectiveness of human motion, is based. And then I will discuss how these elements are illuminated by more recent literature and how they have been applied into sports science, particularly in the context of swimming science. And the second part of my answer will discuss this link between physiological data that is not presented in the thesis manuscript, linking lactatemia and earth rate with jerk cost. So this will enable us to examine the link between jerk cost and energy cost. I think that the Kelly's paper provides an initial insight into the link between motion smoothness and proficiency, and based on the fact that in 1985, Flash and Hogan proposed the theory of jerk minimization or smoothness maximization to explain human movement in terms of motor control. So this builds on Hogan's 1984 work linking jerk and motor control efficiency. At this stage, I agree with you, the question of energy expenditure and physiological efficiency is not explicitly addressed. So this link is only assumed and theorized, but not demonstrated. So it will be taken up and developed in the motor control literature as an inherent motivation for planning motor actions in simple tasks that are, I agree again, far removed from sporting situations. Incidentally, when I reading your pre-reports, I found this line of questioning rather amusing, as the most direct and explicit link I found in the literature between jerk cost and energy cost was written by you in 2014 and 2024. While I agree that this hypothesis originates from the motor control literature of the 80s and 90s, which focuses on isolated tasks, it also demonstrates the implicit diffusion of this link in sports science and its prevalent application. When exploring the link between jerk and energy cost in recent motor control literature, I came across two studies that I would like to share with you because I think it can be interesting to answer your question. The first, by BOUVET and colleagues in 2011, uses movement simulation and optimal control approaches to show that the cost function which best describes the experimental data is an hybrid model combining mechanical energy expenditure with movement smoothness. And the authors conclude that the complementarity between energy expenditure and motion smoothness is evident. This provides empirical evidence for the traditional conceptualization in the literature of a link between jerk minimization and energy cost. But finally, this paper of Wong and colleagues in 2021 seems to me to be entirely relevant to inquiry, and its title speaks for itself. The highlighted passage in the abstract summarized the overall demonstration and the experimental data presented by saying that here we show that smoothness is actually economical because humans expend more metabolic energy for jerkier movement. The author conclude that human movements tend to penalize jerky movements because of their energy costs. So once again, at this stage, this is the most advanced literature on the link between jerk and energy efficiency that I have found. Nevertheless, it could be argued that these are motor control protocols and therefore decontextualized from the sporting context. Let's therefore take a look at what the sports science literature has to say about this link and about your question. So, numerous studies in the sports science literature suggest this link between degraded motion efficiency, altered neuromuscular control efficiency, and fatigue. However, there is, and I agree with you, once again, a lack of real physiological data to support this, particularly with regard to energy expenditure. Nevertheless, this theory is still prevalent, as evidenced by the introduction to the 2021 paper by Moore and colleagues, which states that smooth movement trajectories are advantageous from energetic point of view, but it's only in the introduction. Kelly's paper in 2019 provides additional insights into the role of movement smoothness in running technique proficiency and position this parameter as a discriminant indicator of expertise level. I found, interestingly, only one paper of 2022 presenting data linking running smoothness and economy and energy cost. The assumption that running economy improves with smoother running pattern is put forward based on the literature, as we are discussed at the moment, but this was not found through the experimental data collected. Nevertheless, this was not the study's primary objective, so the implemented protocol was not necessarily designed to test such an hypothesis. So let's look for the last part of this brief literature review to the swimming literature. As we have seen, the hypothesis that minimizing jerk is linked to greater motion efficiency is based on well-established work in movement neuroscience, but it is only indirectly supported in sports, and especially swimming. Indeed, as you know, the jerk cost was first introduced to swimming in 2019 by Gonzalez and colleagues, and to the best of my knowledge, there is currently no data in literature linking jerk with physiological variables, but I will try to propose you something after. However, Gonzalez stated that reducing the jerk cost for a given speed might be beneficial energetically, as it will lead to smaller energy expenditure. Once again, this is an hypothesis that is not based on experimental data, but rather on the traditional motor control literature that we have reviewed and the Newton's second law. Additionally, there is a wealth of literature on swimming that establishes a link between variations in speed and energy cost. Even if it is not jerk data, I think that we can reasonably assume a strong association between variations in speed and jerk cost. Indeed, some studies, such as those of Barbosa and colleagues, show that smaller kinematic fluctuations akin to movement with reduced jerk are associated with lower energy cost. This finding is widely reported in the literature and is now incorporated into some performance model, as can be seen on the bottom left of this slide. And to conclude this part, the work of Moruso and colleagues highlight the importance of applying force to the water smoothly and progressively in order to avoid these large speed variations and the associated increase in energy cost. Once again, there is an implicit link between motion smoothness and energy cost, but I believe that when we consider the literature on motor control, the sports science literature and the swimming literature together, all of these data argue that minimizing jerk cost may be associated with minimizing energy expenditure and improving the energy cost of locomotion. Nevertheless, the direct link between jerk and energy cost has yet to be formally established, and the pilot study presented in the general discussion of my manuscript is a first step in this direction. Additionally, the M2S Laboratoire and the University of Bologna, represented by Professor Fantozzi, have recently started collaborating on this subject through the current internship of Vittorio Coloretti here in Rennes. And during this internship, we will attempt to collect some energetic, dynamic, and jerk cost data using an ambitious protocol to answer this question. If it's okay for you, I can try to respond to the second part. Maybe it's a bit longer, but if you want, I can present to you some data that was not included in the manuscript relating to the link between jerk cost and physiological parameters. So we will look at the link between jerk cost and quadriceps oxygen saturations in line with the payload study, as well as the links between jerk cost and lactatemia and between jerk cost and earth rates. Unfortunately, I have no data explicitly linking jerk cost and energy costs. However, a master's thesis that I supervised this year explored the concepts of durability and physiological resilience in long-distance swimmers in relation to their regulation of stroke mechanics. Although our objectives were different, we nevertheless collected data on energy and jerk cost. However, it's a master project, so we have a lot of measurement artifacts and small number of subjects, only 4, prevented us from obtaining quality data. Nevertheless, I agree with you, it's a really hot topic and it represents a significant challenge and source of motivation for future collaborative projects, especially with the University of Bologna. So here you will find the data on quadriceps oxygen saturation and jerk cost, calculated at each pool length during a 3,000 meter swim at a constant pace. As you can see, the correlation coefficient for each swimmer is displayed, and complementing the results of the linear mixed model detailing the general discussion of the manuscript. Even when grouping all swimmers together, and taking into account that we suspect oxygen saturation artifact for the crew mass subject due to poor NIRS fixation on the quadriceps during swimming, a high correlation remains, indicating a strong link between these two parameters. Interestingly, this relationship is present in every swimmer on an individual scale, and there are large variations in SMO2 values between individuals, suggesting the need for specific monitoring centered around these variations and not absolute values. However, the ICC in the linear mixed model defines a marginal R square of 0.97, indicating that the proportion of total SMO2 variance explained by jerk cost and individual swimmer is almost complete, and I think it's a striking result. But it also emphasizes the importance of individual modeling. Finally, some additional data here is the continuous visualization of the two parameters over the pool length of the simulated, of the protocol. And the negative association between jerk cost and local oxygen saturation is clearly visible, except for maybe for CRUMA, and provides strong incentive to understand the links between technical regulations and physiological repercussions throughout effort, especially in long-distance events. To show you some new data, I have some data on the links between jerk cost and lactatemia and between jerk cost and earth rates. So using 3 datasets that we collected as part of the scientific performance support for the French junior team and the regional training triathlon center in Brittany.
Thank you.
All of this.
Sorry for interrupt you, but
yes,
I'm completely puzzled with your capacity to structure such a perfect answer to the question of Professor Ludwig Seyfer in such a short period of time. But you have both only 12 minutes left for the other questions from Professor Ludwig Seyfer.
I will go very briefly. We have an almost perfect correlation between jerk cost and lactatemia for this data set. Regarding the earth rate, we have also strong agreement with very high R squared. Here is on another sample. We have once again very high coefficient of correlation, of 0.90. And on this last data set, once again another very strong correlation coefficient. So I agree with you. I have no data on jerk cost and energy cost, but I think that we have some preliminary data that show strong correlations between two.
Okay, thank you for the very well-documented answer. So I have two next questions. Hopefully I can have the time to discuss them with you. The first one is one question I also written in my report, and it's about chapter number 6 in open water swimming, showing, well, in fact my question is to understand if you take into account the potential effect of drafting on the jet cost, because we know that drafting can reduce the metabolic consumption by 10 to 40%, and swimming and taking advantage of drafting might have an impact on these metabolic parameters, but also on the jet cost. So I was wondering when I read this chapter if you, at some point, were able to look at the position of each swimmer in the group to know if he can take advantage of drafting and then exhibit a lower jet cost.
Okay, so thank you for your comment. I will try to be a bit fast for this one. So I agree with you, the literature I've show it, and we mention it in the discussion of the chapter 6, as you can see here. So briefly, I think that possible tactical skills are important to monitor, but we are unable to investigate them. So these tactical skills can intersect with the G1 swimmer's superior technical skills to explain their distant kinematic regulation profile. So currently we cannot distinguish the effect of these two factors, technical and tactical, on mechanical regulation profiles. So integrating contextual data such as intermediate position could be a first step in this direction, but it still be again limited by the temporal resolution of official timekeepers. So we do not provide positioning information during the race with regard to drafting. That is leading position, isolated position, in the leading pack, second pack, things like that. So how can we progress? Currently, I see two possibilities, but very complex possibilities. The first is to integrate a GPS alongside the IMU, as we have done in pretest. However, all swimmers in the race would need to be equipped with one in order to reconstruct the spatial dynamics of the race. And the second is to film the races with a drone, but this will involve lengthy processing times, making it difficult to exploit.
Yeah, another solution is maybe less ecological, but is to just go for an experimental setting, where you implement a different condition of drafting, and you look at the jet cost of the follower versus the leader swimmer. And of course, it's less in it's not in the context of the race, but it's one way to very control how drafting can influence the energetic cost and the jet cost. And I have a last question, which was not in my report. So you showed in your slides both the acceleration in 3D and the angular velocity in 3D, and we can see in those pictures that the signals are quite different when we look at the translation or the rotation. So the angular velocity versus the acceleration. And interestingly, in one of your last slides, I think it was the case study with Logan from them, where you showed that he exhibited a too much pitching action. And yes, this one. So my question was, or is, I think that in most of your studies, you compute the jet as the derivation of the acceleration, Euclidean norm, which means you use the acceleration but not the angular speed. Would it be possible, and what would you guess, if you compute the jerk not in translation but in rotation. So by derivating twice the angular velocity. Do you think it could be useful to go in this direction?
Okay, so it's a very interesting point. We reflect about it sometimes to integrate, but as we are driven by the expectations of the field, we need to focus on single metrics for the report, for the French Swimming Federation, so we decide to only focus on the jerk cost. But on a scientific point of view, it could be interesting, and there are some data in literature that use the angular jerk to detect the stroke phases with an IMU located on the wrist. So we can argue that it can be a sensitive feature to technique. Maybe at the sacrum we can also have some insight about it. So we can try to compute it. We have the data on open water or also on a race in pool.
Okay, thank you, Professor Ludovic. Did you finish your?
I think that we have lost you, Professor.
Is hidden in the other side of the earth, you know. Okay, but anyway, we already took more than 20 minutes, so we are in time to ask Professor Maria Francesca Piacentini from the University of Rome, Foro Italico, to introduce her questioning. So very welcome, be very welcome, Maria Francesca. It's a pleasure to share this jury with you despite the distance, and the floor is yours. You have, as well as Ludovic, more or less, well, between 20 and 25 minutes to talk with the candidates.
Sir, I think that we don't...
you miss everybody?
No,
we
I
don't
think
have
Ludovic talk, but we can't hear him.
Maria Francesca, can you hear us?
Tu vois, on les voit. C'est juste le son en fait. Regarde dans les options s'il y a encore ton son qui marche.
En fait, le truc, c'est que normalement, le son, je suis censé être sur un autre truc qui est parti là. Okay. En fait, je crois qu'il y a... Je me demande si les micros, ils sont pas...
Les micros, ils sont out. Essaye pour que ce soit le son de ton ordi. Et demande-les si t'entendent. Vas-y, essaye.
Can you hear me?
Okay, I think it's good. We have a little problem with the micro. Yes, it's okay.
Okay, so Maria Francesca, Professor Maria Francesca Piacentini, welcome to this jury. Please, you
can you hear me?
Yes. Yes.
Okay. So just to say that I studied jerk in translation and rotation in climbing, and I found a very high correlation between those two signals. But I would obviously climbing is not swimming, so I think it could be interesting to see how they are correlated, especially for swimmers who have a high rolling motion of the body, for instance. Like, let's say, if they have a unilateral breathing pattern with a lot of rolling motion on one side, or even if you are working with parallel swimmers who have arm or leg amputation on one side only, maybe in that case, the jerk in translation, in rotation could be more meaningful than in the translation. So it's just a suggestion.
Okay.
And I think I'm near the end of my questions. So to keep the time, I give the floor to the president. Thank you for your answer. And once again, congratulations. I apologize for not being here, but I really enjoy reading and listening. So I wish all the best for your future.
Thank you, Professor Seifer.
Okay, thank you, Professor Ludovic Seifer. Hope you have a nice stay on the other side of the world, and thank you for your questions and participation at the jury. So we move forward to Professor Maria Francesca Piacentini, as I said before, full professor of the University of Roma Foro Italico. Hi, Maria Francesca, can you hear me?
Yeah, not very well, but...
Not very well, okay. I will try to speak
no,
a little bit.
I think now it's okay, yeah.
Loudly. You will have 20 to 25 minutes to discuss with the candidate, and well, be very welcome to this jury. It's a pleasure to share it with you.
Oh, I kind of lost the last part, but I will jump in. Can you hear me correctly? This is the most important thing.
Yeah, yes, it's good. We hear you.
Okay. I would like to thank, of course, the president. I would like to thank again Professor also Bidot for the invitation to be part of this jury, because I really, really enjoyed reading the manuscript. I may be repetitive for what Professor Seifert before me said, but I think I have to acknowledge the great work that Antoine did in these 3 years. First of all, because of me as a sports scientist, it's always very nice to see how the research really embeds into the fields of top-level sports, which is always the most difficult part for the sports scientists, to really breach into the world of high-level sports and to collaborate with high-level teams. So congratulations for this. I think the novelty of the whole work is, first of all, giving an overview from like 25-meter sprint to open water races, with all the difficulties that has. And for the first time, to try to find an explanation specifically for the long distances on pacing, embedding pacing and the technical specificities of each swimmer. And I think that is a very, very novel insight. I'm very happy that open water swimming is more thoroughly studied, because it's an Olympic discipline since 2008, but it has been a bit neglected for a long time. First of all, because of many difficulties also in studying it, and I think it merits a lot, despite the fact that also the formats are now changing continuously. Now you will have to study the 3-kilometer knockout race as well. That's recently introduced in the new race formats. And I think also the statistical models you have been using are very sophisticated and really help also understand better the world of swimming. So this is my premises. Now I will go with some of my questions. Some of them actually, I will be maybe a bit shorter, because some of them have been already asked by Professor Seifert. So, but actually, your toolbox, the toolbox that is the main, let's say, aim of your study, is very biomechanically oriented. So I was wondering, how would you implement your toolbox so as something you need to give rapid, let's say, answers to the coaches with physiological or psychobiological measures that are a bit neglected in your thesis?
Okay, so I think that the starting point of this PhD thesis is the Neptune project and the requirements of the federation that need tools for race analysis on field. So our job has to develop in situ motion analysis solutions, but interestingly, and you are right, know that it is possible. The next discussion with the French Swimming Federation is to include more physiological assessment on board during swimming. So we have tried something with the MOXIE, with the NIRS, to cross the stroke mechanical regulation with the physiological measurements. But unfortunately, I think that open water swimmers will not agree to wear the MOXIE during real competition. So for now, we are restricted to race simulation. Another point of progress that we have identified is to perform physiological assessments during specifically designed protocol to test durability and physiological resilience, and to link them to the profile, as can we see in this slide, in the profile of regulation of the top performers. It's evident that under this ability to regulate the stroke mechanics, there are physiological skills, physiological profiles that enable us to regulate in such a way. So if we have the possibility to continue this work, I think that it can be the next project to cross this data with physiological assessment.
Well, thank you. So I will go to my next question that you actually a bit anticipated. Durability is now a really hot topic in endurance sports because it has been a bit neglected. What tests, I mean, you propose in your discussions a 3,000-meter test, as you showed also now in your last slides, as a test for durability. But do you think that really gives you an insight of durability, or would you propose something different to the open water swimmers as tests to do in the swimming pool?
Okay, so to answer this question, I think that we have to start from the field. And now the open water races in some years switch from a really conservative approach to a kind of performance model like in marathon with very high speed, even at the beginning of the race. So I think that trying to transfer and apply the model of critical swimming speed in swimming can be interesting. And for that, exploring the concept of durability can be interesting. And it was the idea of a master student project this year, in which we perform a 200-meter all-out, then a 5,000 meter at 82% of critical swimming speed, and then we repeat a 200-meter all-out. Unfortunately, we have only 4 subjects, but I think that this kind of protocol can be probably the next way for the swimming research to link the mechanical regulation and the physiological profiles. I personally think that durability and use of critical swimming speed model can be a game changer for technical staff to analyze races, and also for swimming research to help them in this way.
Okay, thank you very much. My next question is a bit on pacing strategies. It's true you were the first one with your studies to link the specific, let's say, technical individual skills to the ability of pacing correctly during specifically long races. But there are other factors that affect pacing again. So pacing is also physiological driven. It's how your brain a bit, let's say, puts fatigue together. So how much you're fatigued at that point of the race. So my question is, if on the open water swimming, do you also have an idea on their nutritional intake? So how often they actually, for example, implemented with carbohydrates during the race? Because that might affect a bit also their fatigue levels and their pacing.
Okay, so if I understand well, your question is about the intention of pacing of the swimmer?
Yeah, it's actually both. One is if you, specifically for the pool races, if you have some data also on perceived exertion during the race.
Sorry?
If you have data on RPEs during the 5-kilometer race.
No, we have no this kind of data. I understand that probably you will refer to the work that you conducted some years ago on 5K with RP that are taken during the race. We are conducted this measurement during official competitions, so we can stop the swimmers to take this. We have some Earth rate data because some swimmers agree to wear a Polar OH1, but we have not enough sample to exploit it, and this is the reason because we try to in this project to go toward the concept of critical swimming speed, to have a bit of physiological dimension, but I agree it's only the beginning of this idea.
But just a comment that when we took the RP, it was on like yours, it was the official Italian 5K championships. We asked athletes to recall after the race their RP kilometer per kilometer, because it is known to be a very reliable measure, also collected after the race. So I think this could be interesting data to link with your technical parameters and your pacing parameters as well, because it's a very strong predictor also of pacing strategy, the perceived exertion. So this is just a comment on the side. Let me see. Yes, I was also wondering if in the studies you did on open water swimmers, swimming, when you had, you analyzed different races, and you divided the groups based on the positioning of the athletes, correct?
Yes.
So, yeah, so it's just out of curiosity, were some athletes, because they're the same athletes that were measured multiple times, so did it happen that the same athletes was once in one group and once in another group? That's my question.
Yes, so it's something that we have not controlled for the initial publication, because we have a low sample size. As you probably know, it's very difficult to collect this kind of data, and we are restricted to the swimmers from the national team. So obviously there are the same swimmers in the same group. But something interesting that we have found is that for all kind of distance, 5, 10, 25, men and women, the profiles, the mechanical profiles are the same for all of these race distances. So yes, it's a limit from a scientific point of view, but it's for us the only way to provide an easy-to-use model for the French Swimming Federation. And now that we have more data, we have around 60 races, I think. Maybe we can improve the methodology. And in this aspect, in the publication, we use a different way to model the stroke regulation profile that we have now improved based on our experience.
Yeah, I agree with you. It's the only way. If you work with top-level swimmers, of course, there is a limitation in this, but I think it's a very important work anyway. Probably my just last question. Since, again, in open water swimming, there are more athletes now that are coming from the pool. So more athletes that are doing both 1,500 meters and or 800 sometimes, and open water swimming. Did you happen, within all the tests you have been doing, to measure the stroke regulation of the same athletes in the pool and in the open water, and if you see a similar pattern, or I don't know if you understood my question, but
yes.
And how does it change? Yeah.
Yes, so it's definitely a very interesting question, and we don't have for the moment a thing to do this, but maybe we can. I don't really know if we have enough data on open water races and pool races. But regarding the evolution of the race dynamics in the open water races that we have discussed previously, I think that it it can be very interesting because now the open water races are more near from the pacing and the technical regulation of pool races. I have just some data with the French Swimming Federation. We try to conduct this kind of descriptive performance model for pool races. So we have around 20 races in N800 meter in pool. And we have also this kind of reverse G shape in stroke rate and jerk cost. So you're right, there are probably very strong link to explore between them, and maybe to classify if a pool swimmer can effectively translate from open water. Yeah. And the case of Daniel Wiffen at the last Olympics is striking in this way.
Thank you very much, and again, congratulations on your extensive work, and I am finished with my questions.
Thank you very much, Professor Piacentini. It was a pleasure to hear your questions. Thank you for your contributions. I hope to see you soon in another occasion, and eventually in person. So thank you once again. So now we will progress to another Italian professor, Professor Silvia Fantozzi from the University of Bologna. Hi, Silvia, can you hear me?
Yes, can you hear me?
Yeah, fantastic. So it's a
Perfect.
pleasure to meet you again, once again at distance. I don't know if the last time we were together in a situation like this was in Switzerland, in Lausanne.
Yes, that's correct.
Or in Eindhoven, but okay, or in Amsterdam. Yeah, okay.
Now I miss your voice.
But always discussing accelerometers and wearables in swimming. Okay, so you have 20 to.
I'm sorry, I miss the last part of.
Yeah, no. Just saying that we were always discussing wearables and accelerometers in swimming. So let's progress with your questions to Antoine, which is the main issue today, okay? You have 20 to 25 minutes to discuss your points with Antoine, okay?
Okay, thank you very much for the introduction, and it's really a pleasure to be here. And thanks for inviting me to be a part of the jury. And yes, I really appreciate reading the work of Antoine. So it is a huge amount of work, and I'm adding my congratulations to your work, to the supervisor. So yes, it was really a pleasure to read all the chapters, and also I enjoyed the conclusion part where you recall all the contribution from methodological and giving also the interpretation and how it can be used directly in the coach's field. And I believe that it is a great work also because you really first of all provide the device in a context that they simply use the stopwatch and don't want to use any technology to the swimmer. So first of all, there was this wall to be that you break. So good work, and also not only from the use of a device on a swimmer, I believe that also you find a way to use another parameters that coaches never use, like jerk cost. They never use these terms, and now they use it. And actually also like in Italian Federation, they start to use it and try to understand it. So I believe this is really a great achievement, I mean, in a scientific context. So congratulations, first of all. Some question. First of all, as an engineer, I would like to know something regarding the device. So do you have any technical specification that you required for the device? Like it must be, or do you investigate it, the minimum value of sampling frequency that you require for the analysis, or the range of acceleration that you suggest to use in the context?
Okay, so I will try to respond to your interesting question, knowing that it's really definitively not my field of expertise. But we use a commercial sensor because we are driving by the fact that technical staff can use them. So we turn to the XN sensor because it's really user-friendly, and the practitioners can use it for monitoring. So for example, in the meeting of the Mare Nostrum last week, I sent sensors to the staff of the INSEP and then use them. So we are really guided by the ease of use. Regarding the technical specifications, we set the accelerometers at a range from minus or plus 8G. But to be really honest, I think it's sufficient for swimming motion, and especially at the sacrum. If we would like to improve maybe the setup and use wrist-mounted sensors, maybe we have to increase it. But it's definitely not my field of expertise, I'm sorry.
Okay, and actually with that sense, you could also use the acceleration without G. But you choose to not use it because I just was the question, you don't trust with the results. Is my guess right? Or
so we can use the corrected acceleration only if we record the data on local, so on the device. So it can be suitable for lab assessment in a range of 20, maybe 30 meters. But for swimming, it's not possible. And it was one of my points of discussion in the manuscript. If one day we are able to have the true acceleration, the insights will be more interesting, because we can really see where swimmers gain speed or lost speed. But it requires major methodological development to do this. Maybe from the engineering point of view, maybe from the artificial intelligence based, if we are able to record corrected acceleration with acceleration from the XNs, for example, we can try to compute a model to perform regression from one to another. So I think it can be an interesting future way of work.
Okay, thank you very much. And did you have any recommendation during the setup of the IMO? I mean, if someone put the IMO in not precise, how much the operator must be precise in attaching the IMO on the pelvis?
Yes, so it's a question that some people asked. We choose the sacrum because it's a convenient location, and the motion at the sacrum is very global. So if we fix the sensor some millimeter to the right, to the left, or things like that, it will not impair the analysis, and our deep learning model to able to recognize the activity are sensible to this kind of problem, and can deal with it to be generalizable. Regarding the modeling of the kinematic variability, I think that it's not a problem, because once again the movement at the sacrum are very global, and we use statistical modeling, so it can remove a kind of noise that can be due to this sensor alignment. Definitively with swimming research application, we make particular attention to this sensor location. When we use with the French Federation, sometimes swimmers have already the swimming suit, so the placement of the sensor is as we can.
Okay, okay, thank you. And so did you already implemented your algorithm with in a situation where someone else acquired data and then give it to you the data, so that you can test in an all-out test the accuracy of your algorithm? Or
I'm not sure to really understand your question, but if it's about the use, the collection of data by other people and then send us the data and we process them, yes, it's how we work with the French Swimming Federation. So it's the interesting of this toolbox is that it's really easy to use for practitioners. Potentially the way of improvement may be for me, for the processing of the data, because no, I'm the only one to have the algorithm and the code, and it's a bit of cooking. One process on MATLAB, another on Python, and the final on RStudio. So maybe the next way, maybe to work with informatic, maybe to work with engineering person, with informatic people to develop a beautiful AirShiny or thing like that to integrate the data.
Yes, the question was more related on the using a validation test of your machine learning process with other type of data.
Okay, sorry. So yes, in the development of the model, we use a holdout subject cross validation, performing just a holdout subject validation, because performing a cross validation with deep learning is very requiring in terms of computation. So, for example, learning the model on my computer take 13 hours. Sorry. So we, for the moment, we can do it, but yes, it can be a way of improvement. But for using it since a few years, it's always work. Sometimes I have to correct the prediction of the model, but it's sufficiently accurate for using with a wide range of swimmers. And the more the swimmers are elite, the more the model are accurate.
Okay. Thank you very much. And actually, this last question comes from the fact that I'm not an expert at all. I mean, of FDA, functional data analysis. So I was just trying to understand the difference between the simple, let's say the elaboration that I typically use with my data. So when you compare the acceleration in maybe it is this just because just make me the question and then I try to see your slides. So my question is, if I use my acceleration and segmented the stroke cycles, and then I report mean and standard deviation of anteroposterior, mediolateral, and longitudinal acceleration within the stroke cycle and compare with your data of FDA, do I find something different or not?
Okay, so yes, it will be different for the simple reason that using FDA approaches, we can see it like SPM. It's maybe more widespread in the biomechanical community. Using the FDA allows to preserve the continuous nature of the signal, and then we can reconstruct the temporal pattern of the data and model the intracyclic variability. So it's the curve that I presented with the intracyclic part and the intercyclic part. If we just compute discrete features like mean, standard deviation, we will reduce the information of one cycle to only a discrete point. So I think that we have to capture this information because the expertise of swimming can be related to the temporal aspects of the cycle. For example, with the French Swimming Federation, we find on the data that there is the integration of the bracing into the motor pattern is the striking, the most important and the most improbable parts of the swimming technique. So if we use discrete features, we can model it. If we use continuous methods such as FDA, such as SPM, we can try to reconstruct this temporal dynamics.
Yes, I agree with you. The comparison was for me of using SPM or FDA, or maybe we can use SPM on FDA. I don't know. I just wondering, not using the discrete point at maximum or minimum. I completely agree with you, but just looking at the pattern with SPM or looking at the pattern with FDA, what gives FDA more with respect to?
So I think that for this comparison between SPM and FDA, we have the results on this slide. It's because we use a functional decomposition into functional basis. then we can use these coefficients to perform clustering, as we have done, but also to perform regression, to perform classification. So using FDA opens a way of methodological things that is more wider, I think, than SPM. SPM allows to compare curves. It can be very interesting if it's your problematic, but FDA opens a wide of possible that I think it's really interesting. And for example, in the chapter on the 5K and the 400 meter, it's a kind of FDA because we use hierarchical generalized additive models. So we first decompose the data into functional basis, and then we perform regression to reconstruct pacing and stroke profiles. And I think that you can do it with SPM.
Okay. So just last one. If I have time, I lose my the minutes. Can you show the results of 10 kilometers in when your subject was about it was CMJ and SES? Okay, here. So do I have time for this question? I don't know. Yes?
Yes, Sylvia, you have.
Okay, so here we have two curves, and I understand it is something in my mind that is a pattern, and we do not have, but we could have like a variability also in this pattern. So here you're not reported because for the coaches it would be too much confusing to have all this information, but if you put here the variability of the red and blue curves, is this different still will be visible, or will be too much variability with respect to the pattern?
So we choose to focus on the intracyclic part for the scientific performance support because it's really the stroke pattern, so a kind of mean movement, and it was the things of interest for practitioners. Yes, you are right, we can add the intercyclic part. However, here I computed this stroke pattern on the last race lap of the race. And if we add the intercyclic part, it's maybe a too large area because we compute it on a time that is very long. I think that it can be more interesting to do this, and we do this, when we analyze pool races. For example, 100 meter, we can apply this framework on each pool length and then reconstruct both the intra and the intercyclic part. For the open water analysis, it may be too much, and it can be finally it can reduce the information for the practitioners, especially knowing that intercyclic variability at the end of the race can be relevant. So it can confuse the field.
Okay. Thank you very much, and congratulations again.
Thank you.
Thank you, Professor Sylvia. It was a pleasure to hear your questions and discussion. So now is my time, and once I'm the owner of time, well, let's put this again. Timing my intervention. So first of all, Antoine, can I use Antoine as the way of talking with you? Okay, thank you very much. I enjoyed very much reading your thesis, all of it. It was quite stimulating, intellectually speaking. I could and I can give. I can assure people that you studied a lot, you read most of the relevant literature, and you did, in my opinion, something very, very relevant, which was not sticking to the, let's say, 21st century literature, okay? Because that allows you to go back to 1979, to Ingvar Olmer, first use of acceleration in assessing swimmers. And that's a clever attitude that nowadays is somehow rare, okay? And it's a pity because in the old days we have some very, very nice contributions that we should take into consideration nowadays. So congratulations for that. And you cover also lots of relevant literature. I can tell you, so modern literature that after tomorrow, Alexia Fernandes, one of my students that you quoted a lot, will defend her PhD thesis. So you are anticipating the use of scientific data from scientists that are not yet licensed to be scientists. So congratulations for that. And yeah, you are entering the world of the wearables that are about to be starting to be used in competition. We don't know how European Aquatics and World Aquatics and Omega will use that for the show off in the pool, but for sure we can extract some interesting data for animating the competitions. That sometimes might be a little bit boring. But anyway, yeah. In synthesis, I enjoyed very much, and I particularly liked the fact that you use, well, jerk costs and particularly intercyclic repeatability. Also in the line of Professor Ludwig Sefer working now on interlap variability and other things like that. And yeah, I was lucky enough to be in the jury of Gonzalez that proposed the jerk costs, and spent last week with Peter Beck at OMI in the United States, so the promoter of Gonzalez, and we discussed a little bit on jerk costs. So my first question is very, very simple. Is it so different from the traditional concept of intracyclic speed fluctuations?
I think that it's not very different, but when we use IMU, it's more simple to derivate than to integrate the acceleration. So it's the reason why we use them. But it's an interesting question because when we work with federation and with coaches, they ask for how can we have the speed? Acceleration is good, but they work with the speed. So we use the jerk costs for methodological reasons. It's simple to derivate.
Coaches didn't read Ingvar Olmer 1979 study. Yeah, I agree with you, and yeah, but the IMUs have other problems, like the orientation of the IMU. So yeah, it was already addressed by Sylvia. Can you go a little bit deeper on the eventual effects on misalignment on the three axes you consider your kinematics?
Yes, so it's something that we have not explored yet because we are once again driven by the expectations of the field. But it's a problem that we have to deal with. And in one of our contributions, we try to do jerk by axis. And I think that this thing can be
by device axis, not body axis.
By axis of the sensor.
Of the device.
We always work with the axis of the sensor, because we don't want to be dependent on a calibration task or things like that prior to the protocol. But once again, it's a methodological bias.
That was the answer I wanted. Sorry for interrupting you. So the question is, for long we discussed on the relevance of extracting a fixed point kinematics to measure jerkiness, if you want, through speed fluctuations or whatever, instead of considering the center of mass kinematics.
Yes.
So what do you feel about almost not speaking on this issue along a thesis on movement variability in swimming nowadays?
Yes, it can be a point that can impact our data, and we have not explored it. We choose the sacrum because we are near from the theoretical center of mass, but we don't explore it.
So you put it in the sacrum exactly for that reason?
It's
not
one of the reasons.
Not only, yeah. Fortunately, you studied front crawl, because if you studied breaststroke or butterfly, things might be slightly different. So I suggest that we should progress in the near future to compare data from the center of mass and a fixed position like sacrum, as we did for the speed meters and so on. And yeah, I fully agree with you. When we integrate acceleration into velocity, we have problems. Immediately having to choose between centered velocity or other derivative equation, other integration equations. So we recently found quite different values of velocity simultaneously obtained by a speedometer and an accelerometer. So it's, yeah, we have some problems regarding this that we need to face in the near future. But repeatability is a really nice new metrics to add to our knowledge. And jerkiness and repeatability you show that they have a very nice and regular behavior with velocity. Okay? So one of your conclusions when you start studying fast swimming, one of your conclusions was the fast swimmers are jerkiest. So it seems that being jerkiest is good. Is it?
Is it the question?
Yep.
I think that it will depend of the constraints of the task. On sprint swimming, the objective is to maximize speed production at the expense of the energy cost. So yes, jerky motion will be valuable. If we switch to another distance, as we have do, for example, in open water races, and especially at the middle of the race, constraints are different. You have to maximize the stroke economy. And then I think that jerky movement can be not very relevant, as the literature on motor control shows.
And there I do not agree with you.
Sorry?
And in that particular point, I do not agree with you. Sorry.
Okay.
So we can discuss a little bit. And the issue is, look, it's the question of the chicken and the egg. Okay, so you need to be jerky to be better swimmer, faster swimmer, because you swim faster. And swimming faster, for swimming faster, you need to accelerate more, and then you need to be more jerky. The question is, imagine that a poor swimmer like myself can swim at the fastest pace as the world record. I will be jerkiest or smoother than the world record holder at the same velocity, at the same maximum velocity.
It's a very interesting point. I think that you will be jerkier because we have to interpret
Sure.
the jerk.
I will shake my brain and I will be quite confused at the end.
We have to interpret the jerk regarding to the velocity.
Yeah.
And that's why we introduce the mechanical proficiency score.
Heteroscedasticity. What does this mean to you?
Sorry?
Heteroscedasticity.
Of the data?
Of the data, yeah. Particularly the relationship between jerkiness and velocity. Because we published a paper, I think one of the few that you didn't read, with Tomohiro Gonjo and Ross Sanders on the issues related to speed fluctuations. So if you measure intercyclic speed fluctuation using simply the coefficient of variation, or variation coefficient, so the standard deviation divided by the mean, you will have a huge influence of the mean velocity. You can compare data obtained at low velocity with data compared at very high velocity, because velocity is determining the variation coefficient. It's exactly the same with your mechanical proficiency score. Exactly the same. So this problem wasn't solved. There's a relativization to velocity, but this matrix is still sensitive to variations to contexts of different velocities. So how do you imagine we can solve this in the future?
So, not for the moment, but I think that it's something that we have to think in the future, and the MPS score that we introduce is maybe a first way to deal with it. And I have some unpublished data that show that an increase of the MPS or a reduction of the GERCOS for a given velocity are associated with a reduction in lactatemia. We work on it with Caroline Jouis for the preparation of the Paris Olympics. Is just some insight for the moment about it.
We will work on that also in the near future. So eventually we can do that somehow together. But I have another question following this, which is a relationship between speed fluctuations, jerkiness, and energy cost. And you know, I was quite fortunate to be the first to empirically show the relationship between both variables in swimming in 1993 actually. So at a given point in page 203, you say that is important, jerkiness is important to save energy, which is important for long-distance swimmers, and you quote Professor Paula Zamparo on this. Do you think that in competition we really save energy?
I think that it depends on the phase of the race.
No, we never. I can tell you this as a coach and also as a scientist, I hope. What we do is to maximize the power output from a given energy input provided by our supportive systems. So we don't want to save, we want to extract the highest mechanical power possible from that physiological and biochemical input.
Okay, so I will change my response. The idea is to maximize the transfer of smoothness degradation into speed.
Of course. And that is also important for 10K, 5K, 400 meters, 100 meters, and 25 meter sprint. It's exactly the same problem. You need to be as economic as possible to excel in whatever distance you consider. Because as much economic you are, being able to extract the convenient power, and of course this is a key issue, okay? And that power is different in 35 meters and in 10K, also physiologically speaking. But what you have is to have the ability to extract the highest power during that period of time from the energy available. And that implies smoothness, and imply also efficiency, and imply also reducing drag. And these are the key factors that, for instance, Professor Paula Zamparo, following Pietro Di Prampero and David Pendergast and other normally states, okay? So, I think that we have that tendency, and particularly coaches, oh, swimming economy is very important, but for long distance races, not for fast sprint. Fast sprint is power. Okay, but we can generate more power if we have more energy, and if we are able to transform into mechanical power the energy we have available. And that is energy cost. Okay, and that's energy cost. Okay, so coming to the end, I have another issue, an important issue, a French issue, or a French-Portuguese issue if you want. You did a fantastic contribution on chapter 9 on sustainability of the critical swimming speed, or as close as possible of the critical swimming speed. And you said that you use the 200, 400, 800, and 1500 method proposed by Wakawashi, but you quoted Jean de Kerle. So it's a kind of nationalism there, because it was Wakawashi who proposed that before Jean. I was in the jury of Jan also. And Jan proposed a short version, 200 and 400, to extract critical speed. And based on that, she later on began proposing that critical speed is a higher swimming speed compared to an aerobic threshold, and it is somewhere between an aerobic threshold and VO2 max, and that will impose the definition of a new intensity zone for training purposes, which in my opinion is completely wrong. So, yes, with all the respect for Jan, a good friend, and Patrick Pelayot, his promoter, you notice that the swimmers swam as close as possible to the critical swimming speed, instead of above the critical swimming speed. Don't you think this is strange? Don't you think that the swimmers should give a little bit space to the anaerobic permanent contribution, eventually, as you showed, not from the beginning, but during most of the event? Okay, so to try to respond to your remark, I will try by saying that critical swimming speed is only a model, and as a model is naturally wrong. But I think that it can be a good practical approach to analyze pacing and races. Regarding the 5K specifically, it's for elite swimmers an effort about around 1 hour, and I think that physiologically is too demanding to maintain a speed higher than the critical swimming speed. This year, I supervise a master thesis in which we perform time trial, time to exhaustion at critical swimming speed, and we have time ranging from 5 to 12 minutes. So I agree with you, critical swimming speed is definitely not a speed that we can maintain indefinitely. We have to know that. But that I think it can be an interesting tool to analyze pacing. Why not using an aerobic threshold? It's for economic reason. It requires lactate tests, and we can do it. Okay. So I still have, we still have 2 minutes and 2 seconds. And the last challenge was, well, I can't escape to this. I was in Omaha last week with Nicolas Tergiou. Okay? So perhaps you know him. He's crazy about nonlinear measures like entropy, fractal dimension, Lyapunov exponent. And those are, I know, non-continuous, so discretized approaches, but with long time series. And you have, with the sensor, long time series. Why did you choose not to use this kind of approach? And this is my final question, with my compliments and congratulations. Okay, thank you. So I firstly tried to compute correlation between sample entropy and final performance on the 5K data on pool and on open water. We decided to not use it because I think that going toward continuous method, it's really a hot topic and a necessity in biomechanics to reconstruct the temporal dynamics of the motion. But in our proposition, I think that there is a strong link between the intercyclic variability and especially the temporal aspects of the intercyclic variability and the sample. Sorry to interrupt you, just to add a comment. You are sampling at 60 Hertz, so it's not continuous. Sorry? You are sampling acceleration at 60 Hertz. Yes. So it's not continuous. Yes, but we can't have a real continuous assessment of the acceleration. And I think it's at least better to use functional data analysis to analyze variability that perform discrete measurements and reducing all the points to only a single one.
But sample, maybe for scientific support to performance, it's only one metric. Maybe we can use it with swimming practitioners.
Thank you very much for the thesis, the presentation, and the answers. It was very, very nice to discuss this with you, and you were quite proficient answering my question. So now we are moving to your promoters. So I'm asking Professor Salima El Kolei from the University of Rennes.
So thank you very much, Antoine, for your presentation. So in fact, I have no question, but just a short feedback on your work. So I was very happy to supervise your work. So you were very proactive during your thesis, and I was impressed by your capacity to understand very well some new concepts in statistics and to adapt them on your data. So thank you very much for your good energy and your dynamism and your motivation during this work. So thank you very much, Antoine.
So, quite fast. So, Professor Nicolas Bidot.
Okay. I will first of all thank all the members of the jury who accepted to participate to this jury, because you are really internationally recognized scientists. It was somewhat chaotic in the organization until yesterday evening, but finally we are here. And we are really pleased about your examination, your remarks, the question you asked to Antoine. I will address some words to Antoine. I know you from your undergraduate degree. I know that you share the same passion than me about swimming, but also about research. But I can say that you had your own conviction, that you love scientific approach in swimming, even in the lab. But your first motivations, even long time ago, was how can I set protocols and analysis that could improve the scientific support to performance. So few years later, I can say that you can be proud of what you did. You gave some answer. There are long other questions you have to solve, but at this time you gave some answers, and you are consistent with your previous questions. I will also say that it was quite specific thesis, because you was at the crossroads between two worlds that are oftenly struggling, academic research and scientific and sport performance applied to very high level. So I can say that you checked all you had to do from an academic point of view. I know that you're ready for an academic career, I'm sure. But I will also point out that you spend lots of time writing reports to staff for the federations. And that's the way in which you were accepted for long and several monitoring assessments at the end of the project, and even beyond the project, because you mentioned some measurements are still conducted during international races. I would like to say that also that you were one of the first students within DigiSport environment. It's important because we are both labs and several, how to say, experts in different domains, but you combined with very great satisfactions both domains, and it was really pleasant to work with you. You really did the job, as we can say in French, and I know that you are able to speak with data scientists, but also with very applied sports scientists, and there's only few people in the world able to do that. I would like to mention this. And finally, I will say that as many PhD thesis, it's not only a job, it's kind of adventure we had together, and for me it was very short, even too short, because it was really pleasant to work with you. You have grown in the process. We worked very well together, and I really hope that we will continue working together, or whatever you are going in the coming months and years. So congratulations, Antoine, and thank you.
So I'm sorry, I think I changed the order of the promoters. So I asked the promoter first, and now I will give the word to Professor Mathieu Marbach. I noticed your contribution on the only paper you signed, I think, on the thesis. So the floor is yours.
So thank you, Mr. President. So first of all, I want to thank all the members of the committee for their time, the accuracy of their question, and the kindness of their comments. Of course, I have no question today, but I will take time to say some words. And because it will be kind words, I would like that your family understand it, so I will switch in French. Donc nous, ça fait 4 ans, je pense qu'on se connaît, mais un peu plus. La première fois que je t'ai vu, je donnais un cours de analyse de données à l'ENSAI, et c'était la première fois qu'il y avait des étudiants digisport dedans. Il y en avait 3, au bout d'une heure, il y en avait 1. Les étudiants de l'ENSAI sont restés. Et Antoine a fait l'ensemble des cours. À la fin, j'ai fait un examen, et ils avaient 2 semaines pour faire leur projet. Je rentre dans mon bureau et je reçois un email d'un étudiant, Antoine Bouvet, je dis qui c'est celui-là, qui m'explique que mon examen n'est pas du tout adapté pour lui et qu'il ne va pas le faire. Et à la place, il se propose d'analyser les données qu'il a avec les outils que je lui ai fait dans le cours. Bon, je dis, bah, lui, il est gonflé quand même. Donc je lui ai dit, bah chiche, mais je ne vais pas te louper. Bon, il a eu 18. C'était d'une qualité d'un rapport d'étudiant de fin d'études de l'ENSAI, alors qu'il avait fait 8 séances. Ensuite, on s'est un peu perdu de vue. Il y a eu un data challenge organisé à l'ENSAI, où il y a principalement des statisticiens qui viennent, mais pas que. Antoine est venu, il a gagné le data challenge. Bon, je me suis dit, lui, il vaut peut-être le coup. On va discuter un peu. Et c'est comme ça qu'on a commencé la thèse. Et en fait, toute la thèse, ça a été ça. Il s'est mis des défis et il les a relevés haut la main, quoi. Donc, je dois dire que je suis assez impressionné de ça, de cette capacité à aller des questions appliquées au sport, de sortir des questions fondamentales de sport, d'aller les traduire au niveau modèle, au niveau stat, machine learning, et d'en sortir aussi des questions plus stat. Et ça, il y a beaucoup de chercheurs qui n'y arrivent pas. Et toi, en thèse, tu as réussi à les publier dans une des meilleures revues de statistiques appliquées et plusieurs revues de sport que je ne connais pas, donc je ne peux pas donner la qualité, mais ça m'avait l'air très bien, notamment au vu des rapports. Donc, vraiment bravo, j'espère que tu vas garder ça. Je pense que c'est dû à beaucoup de motivation et c'est bien. Garde ça, garde cet intérêt et toujours cette curiosité, et je pense que tu as tout ce qu'il faut pour faire un grand chercheur. Voilà.
Merci beaucoup.
Et bon, merci, nous sommes presque au bout de cette défense de doctorat qui allait très bien, dans mon avis. hein. Je ne m'anticipe pas au jury, mais de toute façon, dans mon avis, c'était très bon. J'espère qu'on peut avoir des opportunités de travail ensemble dans le futur, éventuellement en France, ou pourquoi pas à Porto. Hein. Et bon, ça c'est la compétition entre les groupes. Merci pour la participation et l'attention au processus. Et maintenant, on va se retirer pour décider sur l'acceptance ou pas de cette thèse. Bon, je vous remercie à tous. Bonjour. On reviendra pour annoncer le résultat, je pense.
Je vais donner quelques précisions en français, juste pour le public. En fait, pour des raisons techniques, parce qu'on a les gens en visio, on va faire l'inverse, c'est-à-dire qu'on va demander aux gens, au public de sortir. Nous, on va délibérer et on vous appelle l'annonce. Voilà. Merci.